So what I want to do today is I want to start off by doing some applications of probability. I want to talk about the marriage problem. There are lots of versions of this. It's often called the secretary problem. We have a guest here today. He is recently happily married, but just in case things don't work out, he did want to come to today's lecture and learn backup plans. So we're exchanging class visits. It's one of the nice traditions Williams has. One of my former probability students has promised that he will choose his spouse using what I'm about to teach you today. For the record, he was one of the earliest students I have taught probability to and is still unmarried. So be a little bit careful with this. All right? So when you're trying to get married, what is your goal?
To not get divorced.
Wow, it's amazing how things have fallen. Have you seen the movie Enchanted? Who's seen the movie Enchanted? Okay, in Enchanted, they actually do have that conversation that, I consider the marriage as a success if it doesn't end up in a divorce. Now, admittedly, he is a marriage divorce attorney, so he does have a slightly different view. I'll go to the classical definition of success is finding the best person for you. Okay, so we will consider a very binary world where you either get the best person or you do not get the best person. So a success is best person. Anything else is a complete failure. Is this reasonable? No. A lot of times, if you end up with the second best person, not so bad. Much better than ending up with the absolute worst. Okay? So, goal, best or bust. All right? You only care about ending up with the best person. Now, in order to make things interesting, we are going to show you people one at a time. And when you see the person, you have to either say yes or no. And if you say no, that person is unavailable to you from that point onward. They will not come back. Is this a reasonable assumption? Not going to get into that on a college campus. We will assume that once you pass on someone, they move on to other alternatives. All right? So we will put a person here. This is supposed to be, here in a woman. Call her Lorraine. And she is going to be seeing people one at a time. How many people will she see? N, excellent. Right? This is a math class. Sees N people one at a time. And each person she sees, she has to make a decision, yay or nay. Okay?
When she says yes, does that mean that they get married? Or
They get married.
Okay.
And if she says no, then the person is unavailable.
So she's all of their first choice?
Yes. She went to Williams. Twice. Okay, so she's going to see the people one at a time, and if she says, will you marry me, they will say yes. We'll talk later as to whether or not that's a reasonable assumption, but let's do something simple. For people who are looking for colloquium projects, I had a great talk a couple of years ago on Valentine's Day where somebody looked at generalizations of this problem. There's a lot of great things you can do. She needs to come up with a strategy. So she's going to see the people, and then she's got to come up with some kind of rule as to decide when to stop. She does not know the distribution of people ahead of time. Okay? If you knew that the best person was Prince Charming, and Prince Charming is going to be coming through eventually, well, you just wait until Prince Charming comes. She doesn't know who the best person is. She can just compare people to people she's already seen. Can somebody give me a good strategy for her? Always say, well, if she always says yes, she's going to take the very first person. What's the probability she gets the best person if she takes the first person?
Does she get to leave when she says yes?
As soon as she says yes, she marries that person, the game is over. If she takes the first person, what's the probability she gets the best person? If she takes the third person, what's the probability she gets the best person? If she takes the third person, what's the probability she gets the best person? It's also 1 over n. The best person is equally likely to be anywhere. So if she chooses a specific spot, always, without looking, all right, I'll take you. Her probability of getting the best person is just 1 over n. The question is, can we do better, and if so, how much?
Wait, if she's taking the third person, hasn't she already seen the first and second person?
Yes. But I'm saying she could just make her rule, no matter what, I'm always going to take the third person. And if she has a rule like that, her probability of success is only 1 in n. If n is large, this means she has a negligible chance of getting the best person. We want to give her a better strategy. Can anybody think of a better strategy?
You gotta rule people out.
You got to rule people out. How?
Like if you see the first person, you can definitely be like, that's definitely not the best.
How do you know? You don't know the sample space. It could be the first person is the best.
We look at the probability the first person is not the best.
Probability the first person is not the best is n minus 1 over n. So this is a difficult question. How would you, yes?
Oh, sorry, you would probably the first, like the best person's in the first n people, and so like.
So the probability the best person is in the first 5 is 5 out of n. Best is in the first 8 is 8 out of n.
If you come to a person and they're better than all the people you've seen before, then the probability that they're the best is higher.
Okay, so let's make a cut. She will look at first k, take the first one better. So what she's going to do is she's going to spend a little time sampling the field. And she'll just evaluate the first k people, and no matter what, she will not take any of the first k. And then she will take the first person better than the best person she's seen. And we're going to just see how well does this do. There are other strategies. I claim that this is actually going to be the best strategy for her. It's easy to explain, which is a nice feature. What's the probability that she automatically loses with this strategy? K over n. So loses k over n automatically. What homework problem is this similar to? Where have we seen something where you have a good chance of losing no matter what? Not the bags of marbles. The aces up game. This is like the aces up where 10% of the time, just the way the deck is shuffled, you're going to lose. K over n of the time, she's going to lose. Does this tell you want k to be large or small? You want k to be small. So again, what I care about is not having you choose your spouse using this method. I care about the ideas that this problem will lead to. We want to get a sense of what the answer should be. What are the competing influences? This forces k down. Because the higher k is, the greater chance you have of automatically losing. But this is also over here, this is going to force k to be larger. The more people we see, the better estimate we have, and then taking the first person better than the best we've seen, the more likely that is to be the best person. So unfortunately, we have two competing influences for k, and we're going to try to see which one wins at the end of the day. What's nice is this problem is going to involve a lot of the old material from Calc 1. It's going to involve a lot of material from earlier in the semester in probability. It's going to be a great way to review a lot of the things we've done. It's actually going to connect a little bit with the toy box Happy Meal problem we did on Monday. So we're going to let strategy SK is first one better than the first k. So that's the strategy she's going to play. We want to calculate what is the probability you get best given you play strategy k. We'll call it given that you play strategy sk. And then we'll try to figure out which choice of k is going to give us the greatest chance of winning. Whenever you hear something like this, which choice of k, what do you think? What technique might be useful to find the best k? Derivative. Now, unfortunately, derivatives are a little bit hard to use here. Why are derivatives hard to use here? K is discrete. You are not going to see, it's not like a seductive leg coming in or something like that. You are not seeing parts of a person, okay, and then making your decision. You have to see the whole person. K is discrete. We will find a way to deal with discreteness and still use calculus. Right? It involves one of my favorite things that's no longer taught in Calc 1 because this is the 21st century, curve sketching. All right. I'm going to do this as a partition problem. It's going to be the sum, m goes from 1 to n, the probability you get best given best is at m times the probability best is at M. Some of this is very easy. What's the probability the best person is at location M? 1 over n. This is wonderful. This is independent of M. Let's look at the probability you get the best given that the best is at M. There are some values of M where it's very easy to evaluate this. Which values of M are very easy to evaluate? Less than k. Or actually, you can do a little bit better than less than k. Slightly better than less than k. Less than or equal to k. If the best person is in the first k, it's not available. Right? So this person will take the best person, the first person better than the best they've seen. If they reach the last person, they have to take it. Okay? So this is going to be the sum. M goes from k plus 1 to n of the probability get best given best is at M times 1 over n. Okay? So she starts seeing people. She sees Joey. She sees Martin. She starts seeing these people, and she starts evaluating how good they are. And let's say Martin was the best person she sees. Okay? So in the first k, the best person was Martin. She will then choose the first person better than Martin. Okay? So let's draw what's going on here. So here's 1, 2, here's k, and here is Martin. Okay? And then maybe here's a bunch of other people. Let's say the best person, I don't know, is over here. This will be our point M. Call him George. We'll put the best person here. We need M, the best person, to be the first person better than the best person in the first k. What's the probability that the first person better than the best in the first k is at M? 1 over. So how many places are there before here? There's m minus 1 spots. If you look at these m minus 1 spots, if anybody from k plus 1 to m minus 1 is better than Martin, we're in trouble. She won't end up with George. Okay? We want to make sure that Martin is the best in the first m minus 1. What's the probability that in the first m minus 1 people, the best is in the first k? K over m minus 1 is the probability best in first m minus 1 is in the first k. So remember, everybody is equally likely to be in any place. So if we want the best person in the first m minus 1 to be in the first k slots work for us. There are m minus 1 slots possible, so the probability it works is k over m minus 1. So this is the same as the sum, m goes from k plus 1 to n, of k over m minus 1 times 1 over n. I can pull the k and the n outside, and we have k over n, and then we have the sum, m goes from k plus 1 to n of 1 over m minus 1. Okay. So we want to just simplify this algebra a little bit. And I claim this is the same as, k over n if you want the sum m goes from k to n minus 1 of 1 over m. Just shift the index by 1. M is starting off at k plus 1. Have we seen a sum like this before? Where have we seen this sum?
With the price problem.
With the price problem. What's the name of the sum? It's the harmonic. So if you want the sum, m goes from k to n minus 1 of 1 over m, this is the same as the sum, m goes from 1 to n of 1 over m. minus the sum, m goes from 1 to k minus 1 of 1 over m. So this is a really nice trick. To calculate the whole sum, I know a really nice formula for summing from 1 to the end. So this would basically give me the log of, I guess this is an n minus 1, the log of n minus 1 minus the log of k minus 1. And what's the log of a difference? The log of the quotient. So this is the log of n minus 1 over k minus 1. I've got to put a little squiggle here because this is not exactly right. It's not exactly the log, but it's close. And if you wanted to do a more careful analysis, you could put in those lower order terms. Well, I have n minus 1 over k minus 1. If n is large, k is probably going to be large. Instead of n minus 1 over k minus 1, I should be able to replace this with what? The log of n over k. And so we get the probability of the best, given that she plays strategy k, is going to be, we have a k over n times the log of n over k. This is the same as k over n with a negative sign, the log of k over n. I'm just using my log laws again to replace the log of n over k with the negative of the log of k over n, just flipping things. Why do I want to do this? Because this now gives me a new function to study. I'm going to study the function f of x is negative x log x. There have been a lot of times in your calculus classes where you've been given functions to differentiate because they are cookbook problems and you have to do them because nobody cares about them. But we have to make sure you know how to differentiate. This is now a natural problem where a function like x log x is occurring. What rule would we use to take its derivative? Product. Okay, so it would be nice if we had even more boards so we could keep everything in place. I'm going to erase this part over here. I don't think we need the statement of the problem anymore. So we want to figure out where is this function maximized. Now, when we find where the function is maximized, we're going to find the real value that maximizes things. Is that what we want? If we get that the answer is k is equal to pi, n divided by pi, we can't really look at fractional parts of people. We're going to have to somehow pass from a real optimal to an integer optimal. So next year I will probably be teaching a class on operations research where we'll actually deal with issues like this. I'm going to show you how your curve sketching from calculus helps you. So let's let f of x be negative x log x. So if we take the derivative, f prime of x is negative, all right, product rule of derivative of x is 1, so we get log of x. And then we get plus x times the derivative of log of x, which is 1, because the derivative of log of x is 1 over x. So the critical point is f prime of x equals 0. So that tells us the log of x equals negative 1. Therefore, x equals 1 over e. We also have to consider endpoints. Well, if we consider the endpoints, what would be the endpoints? What would be the endpoints? What are the ranges for x? So remember, x is k over n. So what are the extreme conditions? I'm sorry? Yeah, so we could take k equals 1, and this would give us x equals 1 over n, and then the probability of success is about 1 over n. So if we actually plug it into here, it'll be a little bit different. It'll be like log n over n. So if we take x equals 1 over n, this is going to give us negative 1 over n log of 1 over n. Well, negative log of 1 over n is log n, so this will give us log of n over n. This tells us that actually there's a little bit of an issue with our approximation. It's, if she chooses the first person, she should not have a better than 1 over n chance, but it's essentially 1 over n. What's the other extreme she could take? X equals 1. She could take k equals n. And in that case, the log of 1 is 0. Now, if we take x equals 1 over e, at critical point, f of 1 over e is negative 1 over e, the log of 1 over e. What's the log of 1 over e? Negative 1. So this means f of 1 over e is equal to 1 over e, which is about 36.8%. Right? This is absolutely shocking. If she were able to choose 1 over e, so what does that mean? X equals 1 over e. This is the same as k over n equals 1 over e. This means k equals 1 over en. She looks at 1 over e% of all the people and takes the first one better than that. And her probability of ending up with the best person is 36.8%. As n goes to infinity, over a third of the time she ends up with the absolute best person. What if you weaken it and say, what if she ends up with the best or the second best? I believe that's over 50%. If you ask that she ends up with somebody in the top 0.5%, the probability becomes astronomically large. This is phenomenal that you can do this well. If you just choose one person at random, the odds are 1 over n, which goes to 0. Almost 40% of the time, Lorraine is ending up with the best person. Unfortunately, what does she have to be able to do to end up with the best person? Yes. Well, okay, good. So one issue, she does have to know what n is. And so we will later on, if people want to, a really good Valentine's Day problem is to assume n is drawn from a different distribution. Maybe there's a Poisson distribution, something like that, that models how many marriage prospects you will see in your career. You are absolutely right that if you do not know what n is, this is going to be difficult. But there's something else that we're assuming right now when she's making this choice that we're not allowed to do. So we're saying that she should choose k equals 1 over e times n. What can you tell me about that number? It's irrational. Okay? We're not supposed to have anything irrational in marriage, right? What can we do? She can't just choose 1 over e times n people. So what she should do is she should look at the people, the choices of integers immediately before and immediately after, and see how does that do. So what we'll do now is we'll keep the picture. We'll erase this over here. And what I want to do is I want to do some curve sketching. And so we're going to have, f of x is equal to negative x log x. This is the probability she ends up with the best. Okay? So how many of you have ever seen plots like this, where you plot the x-axis, you're going to plot your function, and below it, you actually plot the sign of the first derivative? Do they teach this anymore? This is a great way to get a sense of what's going on. So the key points are 0, 1 over e, and 1. What's the value of the first derivative at 1 over e? 0. Now we know f prime of x is equal to negative log of x plus 1. If x is less than 1 over e, what can you tell me about the first derivative? Well, let's take x to be 1 over a billion. If x is 1 over a billion, the log of 1 over a billion is negative log of a billion. This is going to be a very negative number. When we take a negative, we're going to get a positive. The first derivative is positive if x is less than 1 over e. Okay? So the first derivative is positive in this range here. What if x is greater than 1 over e? What can you tell me now about the first derivative? What's true about the first derivative now? Negative. So if I want to sketch my curve, if the first derivative is positive, the function's increasing. If the first derivative is negative, the function's decreasing. So it's got to look something like this. I don't know the exact shape, but I know I'm increasing up until 1 over e and then decreasing afterwards. So the optimal choice of k is either immediately before or immediately after. And so you just have to check the neighboring points. And this allows you to go from a real maxima to an integer maxima. So 36.8% of the time, she will end up with her density, with her destiny George. Okay? That's not bad. Any questions about this problem? Yes?
That last part that says when x is 1, it's 0, shouldn't that be 1 over n still? If she just randomly decides to pick the last person?
It should be, and this is a slight problem with the approximation we're doing.
That's, yeah.
0 is essentially 1 over n. Log n over n is essentially 1 over n. Yes?
Now, wouldn't you have probability 1 over n if x was equal to k minus 1 over n, not 1? Because if x is 1, then you're choosing the first person after all of them, which is no one.
Right, so okay, so what we should probably do is we should probably then say she can't take the very last person, and the largest value we can probably take is x is n minus 1 over n, and probably put that in. The main thing is, I don't really have to worry about the endpoints once I start doing my plots, because I know it's going to look something like this. And there's going to be some slight issues with the approximations. For stuff like this, I know people were trying to do some simulations with stuff earlier in the semester. If n is small, these simulations are not going to work out well. It's only when n gets large that the sum of the harmonic series, if you sum the first n terms, looks like log of n. For small values, you're going to be off by a little bit, and that will have a major role.
Could you go over the k over n minus 1 part again?
Go over which part?
The k
Oh,
over
this, okay, so this is the hardest part of the whole problem, is, let's say the best person is located at M. In order for her to take the best person at M, if you look at the first M minus 1 people, we need to make sure that she doesn't choose anybody before M. She's not going to choose anybody in the first K. She's going to choose the first person better than everybody she's seen in the first K. Okay? So where do we put the second best person? If the second best person is after K and before M, she will end up with that second best person. We don't want her to end up with Martin. We want her to end up with George. It would be disastrous if she ended up with George. Destruction of space-time continuum bad. It would be horrible. Okay? What's the probability that the second best person of the first M, or equivalently, that the best person of the first M minus 1 is in the first K? All of these slots are equally likely. Think of it as I've got M minus 1 spots to choose where to put Martin. I have to choose one of them. So I have M minus 1, choose 1. That's the number of places to put him in. All of those spots are equally likely. They all happen with probability 1 over M minus 1. So the probability that Martin ends up in the first K, I've got K possible slots. So the probability that Martin ends up here is 1 over M minus 1. That Martin ends up here is 1 over M minus 1. That Martin ends up here is 1 over M minus 1. I have K of them, so I sum them together, and I get K over M minus 1.
So we're assuming Martin is the second best.
We're assuming Martin is the second best of the first M, and we need the best of the first M minus 1, which is equivalent to the second best of the first M, to be in the first K.
So it's not that George has to be at that point, he just has to be any point.
Well, we're saying George is at location M. George has to be at some location. We're going to say George is the best person. So let's call George's location at M. And now let's see what's the probability we end up choosing George, given that we are going to take the first person better than the first K. Imagine Martin was over here, and Martin is better than everybody in the first K. She'll then choose Martin, and she won't get to George. We need to make sure she doesn't choose anybody before George. If George is immediately at K plus 1, we're not worried. She will end up with George. But if, as George moves further and further away, it's going to become less and less likely that she'll end up with George. One way to make sure she ends up with George is if the second best person overall is in the first K. If the second best person overall is in the first K, she will have to end up with George. But we don't really care what's going on after George. We don't need the second best person overall. We just need the second best person among the first M to be in the first K. And once she sees that person in the first K, that's the best she sees. So Martin is the best she sees. She's now fixated on Martin. She won't take anybody who's not as good as Martin. And then she keeps going, she keeps going, she keeps going, and then she fortunately hits George. If Martin, however, was over here, Martin would be better than the best person she's seen in the first K, and then she would take Martin. So maybe what we'll do is maybe Calvin is the third best person. And if Calvin were here, and then we moved Martin to over here, now she would choose Martin. Because Martin would be the first person better than Calvin. Yes?
Over there, when you're doing sigma, 1 over n equals, yeah, sigma.
Yes.
How does it sum when you have n minus 1 as your upper limit value?
I'm basically just using the sum of the harmonic series up to some point t is about the log of t. So here I have a sum going from k to n minus 1. The formula you derived in calculus goes from 1 to n minus 1. So I want to start the sum from 1 to n minus 1. I can't just add in extra terms. I then have to subtract them. And so now I can say this sum is approximately the log of the final. And this sum is approximately the log of the final. And then it's just algebra simplifications from this point onward. Okay. There's a lot of good material in this problem. It applies the conditional probabilities we've looked at. It uses partitions. It uses results from calculus in terms of optimizing functions, taking derivatives. It uses curve sketching to get some sense of how things go. This problem contains an enormous wealth. If anybody wants to use this to determine whom they marry, I would be very interested to see, but again, my student who has said he's doing this is still looking. Okay? All right, any other questions about this? For extra credit, does anybody know what dance this is happening at?
I mean, it's Back to the Future.
Yes, so what's the name of the dance? The names are all from Back to the Future. This is Back to the Future Day, October 21st, 2015. What's the name of the dance for cultural extra credit? Well, not looking too good for the Back to the Future prediction on the Cubs. What is the name of the dance in the original Back to the Future movie? Yes?
The Under the Sea dance?
I think that's correct. It was either Under the Sea or The Enchantment Under the Sea. That is close enough that I cannot correct it, so email me for cultural extra credit. I thought if I had Biff as the last person, it would be a little bit too obvious what was going on. All right, what I want to do now is I want to go to differentiating identities. So this is an extremely powerful technique. We've used it already with the geometric series. And the idea is identities are very hard to prove. They're the bread and butter of mathematics. As soon as you have an identity, you want to milk it and get other identities. Do we have any other identities, any other formulas for sums that we've seen in this class that we've used again and again? Can you think of any other formulas for sums? Well, but I want a formula that gives me a closed form expression for a certain sum. I know how to calculate the geometric series sum.
Like n times n minus 1, n times n plus 1 over 2. Taylor series.
So that's a specific formula. It's a finite sum.
The binomial.
The binomial theorem. So the binomial theorem, x plus y to the n is the sum, k goes from 0 to n, of n choose k, x to the k, y to the n minus k. The idea is we can actually use this to generate more identities. So we can differentiate both sides with respect to x very easily. So let's apply the operator x d by dx. Well, if I take the derivative of this side with respect to x and then I multiply by x, I'm going to get x times n x plus y to the n minus 1. Do I have to worry about interchanging the sum and the derivative?
It's fine.
It's finite. Yeah, life is good. No need to take advanced real analysis for this purpose. You need to take advanced real analysis for other purposes, but here we can interchange the sum and the derivative. It's finite. So we have x times the sum, k goes from 0 to n, of n choose k, k, x to the k minus 1, y to the n minus k. Or if we simplify the algebra a little bit, we'll have a sum, k goes from 0 to n, of k, n choose k, x to the k, y to the n minus k. And this is going to just be n x, x plus y to the n minus 1. So now the question is there a probability distribution that's similar to this? And if so, what should we be thinking about x's and y's? Any thoughts about what we should take x and y to be?
If x is like p and y is 1 minus p.
Good, take x is p, y is 1 minus p. So maybe it's the probability a coin is head. So this is going to give us a binomial random variable. And this is going to be the probability we have exactly k heads. What's the probability we have k heads? So if you have a coin with probability p of heads, let's say you have n independent tosses, let's let x be the number of heads, then the probability that x equals k is I have to choose k of the n tosses to be a head. Each head occurs with probability p, and then each tail with probability 1 minus p. And this will be the probability that x equals k. Now we should be a little bit clear, and we should say what values of k we consider. This is for k in the set 0, 1, 2. I don't care how skilled you are not going to flip more than n heads when you toss a fair coin n times. You're not going to flip fewer than 0 heads. And you're going to flip an integer number of heads. So this is a really nice, good, discrete random variable. The first thing we should do whenever we see a discrete random variable, what do we want to calculate? It's mean. Now if you just think about this, if every toss has probability p of giving you a head, how many heads do you expect after n tosses? Pn or np, depending on which way you like to phrase things. So we already have a sense of what the answer should be. Let's calculate it. So we would get the expected value of x is going to be the sum, k goes from 0 to n, of k times n choose k, p to the k, 1 minus p to the n minus k. The formula we just derived 1 moment ago is now quite useful. And in fact, you can see what's wonderful about taking x as p and y as 1 minus p is what's x plus y? 1. And so when you plug that in, you'll get p, and I'll write it again on the next slide in a second, is equal to the expected value of x. And so just using the, yes?
Where did the k come in the expected value?
The expected value is just the sum of k times the probability of k. This is just the definition of the expected value. The expected value of x is defined as the sum over k times the probability x takes on the value k. And so now if we want to calculate the sum, we use that formula, and we just get its p times n. So exactly what you would expect. If we wanted to calculate the variance, we have 2 ways to attack this. We could calculate the expected value of x minus the mean, and actually take the expected value of the square of that. Or what we could do is we could use one of the simplifications for variance. So another way to write variance is the variance of x is the expected value of x squared minus the expected value of x squared. All right, well, the expected value of x squared, we know how to do this. We just calculated the expected value of x as p times n. We can square that. We need to calculate the expected value of x squared. So we've got the variance of x is going to be the sum, k goes from 0 to n, of k squared times the probability x equals k. And then we're going to subtract off the square of the mean. So we're going to subtract off Pn squared. How do we calculate this? Well, this is the same as the sum, k goes from 0 to n, of k squared, n choose k, p to the k, 1 minus p to the n minus k, minus p squared, n squared. Does this look like anything we know? Yes. We go all the way back to the first board. We took the derivative once, and we got this formula. And we took the derivative not just with respect to x, but then we multiplied by x to keep the power of x at k. And again, this is where you have to decide what's going to lead to the best algebra. By taking this extra x, we keep the power of x the same, so we keep this part over here is going to be the probability density. Okay? If we now want to calculate k squared, what should we do? Do it again. Now it's very important that we first take the derivative and then we set x equal p and y to 1 minus p. If we did that earlier, x and y would depend on each other, and the formulas would become a lot more complicated. As a nice exercise, try to see if you can make that work. That will give you an appreciation for when you should do things. All right, let's do it again. So when we take the derivative once, we end up having this formula. So let's take the derivative again. So now we have x d by dx. Oh, joy. How do we take the derivative of this piece? Product rule. So we're going to have x times the derivative of this by the product rule. We'll get n x plus y to the n minus 1 plus n x. Now when we take the derivative of this with respect to x, we'll get n minus 1 x plus y to the n minus 2. And then this over here will be the sum. K goes from 0 to n of k squared. N choose k, x to the k, y to the n minus k. So the stuff on the bottom over here is exactly the expression we want. And now we take x equals p and y equals n minus p. So we just do some algebra at this point. So if we want to do the algebra, what's nice is what's x plus y going to be? 1. So this is going to be 1. This is going to be 1. X is going to be p. We're going to have a p here. We can pull out an n. So we'll have an np, and then we'll have 1 plus n minus 1 times p, I believe, when all the dust settles. So the tracking is not working again. All right. So let's see if I can come over here. All right. So this will then become p times n, pulling out the n, and then we'll have 1 plus, we've got a p n minus 1 minus p squared n squared. So when the dust settles, I believe that is the expression we have. Have I made any algebra errors, or is this what we get when we plug in x equals p, y equals 1 minus p? All right, so now we just see what happens as we expand. So we're going to get Pn plus p squared n squared minus, have we made a mistake? Oh no, good, minus Pn minus p squared n squared. All right, this is not looking good. P squared, good. I was going to say, good, p squared n, excellent. So the p squared n squareds cancel. We have Pn minus p squared n. So we can write this as p times 1 minus p times n. So there's the variance. So the variance for this problem is just going to be p times 1 minus p times n. If this is the variance, then the standard deviation of x is going to be the square root of p 1 minus p times the square root of n. And this is going to be extremely important later in the semester. We want to get a sense of how things are varying with n. The fluctuations are going to be of the size square root of the number of tosses. For what value of p is the variance going to be smallest? 1. Anything else? 0. If you take the Mobius coin, the coin that's either always heads or always tails, the variance is not hard to calculate. If you always toss a head, how many heads do you expect after n tosses? N. What are the fluctuations? None. Similarly, if you have the coin that's always tails. So whenever you see an expression, ask yourself, is this reasonable? Makes sense. What value is going to have the largest fluctuations? Where is p times 1 minus p maximized? This is a calculus problem. At half. So as a nice exercise, do this. If you want to avoid doing calculus, I don't know why you would want to, but if you want to, you can do curve sketching. You have the parabola p times 1 minus p. It vanishes at 0 and 1. It's downward sloping. It's got to look like this. So here's 0, here's 1. The maximum is at 1/2. Does it make sense that the maximum variance is at p equals 1/2? Yeah. The closer you are to p equals 1 or 0, the more likely you are to have all the coins coming up the same way. So this is just one of many examples of the power of differentiating identities. We start with an equality we know, and we keep generating more and more equalities from it. It's a little bit hard sometimes to figure out what is the best path through the algebra. Sometimes it pays to take 2 pieces of paper and then just start doing it different ways and see which way works. Which way it comes out nicely. If I didn't put in this x, if I just did the d by dx, I would have an x to the k minus 1, and then I would have a k times k minus 1, x to the k minus 2 if I did it again, and you'd have to play some games. Okay. Any questions about this problem before we do the last thing for the day? So we have time for one last thing. There is another way to view the binomial process. So in the binomial process, we're tossing a fair coin we're tossing a coin with probability p of success n times. And the tosses are independent. So we have this random variable x, which we'll call binomial Pn. So p is the probability of a success, n is the number of tosses. Let's let x1 through xn be independent, and they'll be Bernoulli with probability p. So think of x1 through xn as they're just one coin toss, and they have probability p of success. So for these, the probability that xk equals 1 is p, and the probability that it equals 0 is going to be 1 minus p. So p% of the time we get a head, 1 minus p of the time we get a tail. Let's calculate the expected value of xk. What's the expected value of xk? We get a head with probability p, or we get a tail with probability 1 minus p. So what's the expected value of xk? P. This makes sense. If I'm tossing a coin with probability p of heads, I expect to get p heads. And now we use one of my favorite techniques, linearity of expectation. The expected value of x, well, x is just x1 plus xn. If I want to know how many heads do I have, it's how many heads on the first toss, plus how many heads on the second toss, plus how many heads, etc., etc., etc. What's the expected value of a sum? Sum of the expected values. So this is the expected value of x1 plus dot 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 plus the expected value of xn. Well, what do all of those equal? P, and we have how many of them? N. P times n. So here is another way to calculate the mean of a binomial random variable. We can replace this very complicated random variable with a lot of simpler random variables. This is a general theme in life. You would much rather do a lot of simple problems than one really hard problem, if you can figure out how to combine things. You can also use this to combine and calculate the variance. And we haven't proved it yet in class, but it's in the book. The variance of a sum is the sum of the variances. All right, so this is a good place to end for today. My office hours and whatnot for this week have been thrown to whack because I've been visiting a lot of people and covering for a lot of people's classes. I will be in my office probably from now till at least, I think, 2 o'clock. Okay. Enjoy the rest of Back to the Future Day. Go Cubs.